Not safe today, so I'm going to, again, just do this from home and hopefully you can get the gist of this. Today we did something called the alternating series test. We're not going to worry about that one right now. And before I did that, we just kind of reviewed some of the tests we had and why we would use them. It says determine if each of the following series is convergent or divergent. When I look at this series here, you have to make a decision. What do I compare it to? And I should do limit comparison test, I suppose. And it's not a direct comparison because so it looks like 1 over, well, actually, I know that this series, let's do direct comparison. This series looks like 1 over n, and it's always greater than 1 over n because you're subtracting off that cosine squared. So I can use direct comparison, and it is greater than 1 over n, and I know 1 over n diverges, so this series must diverge by direct comparison. So you have to kind of be careful, though, because it's really easy to mess up the tests and figure out which one to do. For example, this guy here, I would compare this with 1 over 3 to the n, and to use, and I know 1 over 3 and 3 to the n is convergent. So I would have to decide, is this always less than or equal to that to be able to use that test? And because I'm adding something, a positive number on the bottom, yeah, it is always less than or equal, so I can use direct comparison test. Now this particular guy here, I want to compare it to 1 over 3 to the n, but this is not less than or equal to it. It can be greater than it. So in this case, I would do the limit comparison test. I would compare it with 1 over 3 to the n because I know, again, that converges. So what I'm going to do is divide the two terms, so 1 over 3n minus n and 1 over 3 to the n. And so it turns into this. And I'm going to take the limit as n goes to infinity, and I get 1. So remember, with the limit comparison test, if the limit is finite and positive, then we know they either both converge or both diverge. So this series converges by the limit comparison test. All right, so today we're going to look at alternating series. And an alternating series is one where you have a plus and minus kind of thing that alternates. It could be written as -1 to the n plus 1. Like this one. So if I plug in 1, I get -1 squared, so the first term will be positive. When n is 2, I get -1 cubed, so then it's negative. And we just plug in the n's over there. So this looks like a harmonic series, but it's alternating sign every time. I could also have -1 to the n. Notice the difference. If I start at 1, the first term is now negative instead of positive. So there are different ways to write it, and in fact, sometimes they'll try and sneak it in there with sines and cosines. If I do sine of pi over 2 plus n pi, when n is 0, I would get 1. When n is 1, I would get -1. So that's a way of sneaking that in there without you noticing it. Or multiplying by cosine n pi, that would alternate every time between -1 and 1. So just keep that in mind when you see it. So just knowing that the limit is 0 tells us very little about convergence if the series. We know if it's not 0, it diverges. That's your divergence test. But it turns out that when it's an alternating series, it must converge if the terms have a limit of 0 and the terms decrease in magnitude. So if it's alternating series and it's decreasing in magnitude and the limit is 0 as n goes to infinity, it must converge. Kind of one of the, well, let's read the formal definition. It said, let an be greater than 0, positive. The alternating series, this and this, converge if the following two conditions are met. The limit as n goes to infinity equals 0, and an plus 1 is less than an for all n. So in other words, it's decreasing. All right, so in words, a series converges if it's an alternating series, if the terms decrease in magnitude and have a limit of 0. Kind of one of the classic examples of this is changing the harmonic series into an alternating series. this is the harmonic series, and we learned yesterday that, or no, I guess 2 days ago, because by the p-series test, this series always diverges. However, if I make it an alternating series and put a -1 to the n out front, we're going to test this now with the alternating series test. So that yes, it alternates. Yes, it decreases in magnitude as n gets big and has a limit of 0. So therefore, the alternating series version of this does converge. So that's kind of a classic example of that. All right. It does not say, this is very important, it does not say that if the limit doesn't equal 0, the series diverges by the alternating series test. The alternating series test can only be used to prove convergence. All right. So I can't use this test to prove divergence, just only convergence. But if the limit weren't 0, it would diverge by the nth term test for divergence, which we already learned way back there. So we have to be careful with our tests. So the alternating series test only tests convergence. So to determine whether it converges or diverges, we're going to look at this. If I try the alternating series test, this is an alternating series because of this right here. The terms are decreasing in magnitude as n gets large. That's true. But if I take the limit as n goes to infinity, remember the highest powers win. So this is going to look like n over 2n, which is 1/2. And this is going to alternate back and forth between positive and negative. So the limit doesn't exist. It's not 0. So therefore it diverges by the nth term test for divergence. All right, not alternating series. The limit has to be 0. All right, so if you look at this guy here, yeah, it's an alternating series. It is decreasing, and the limit as n goes to infinity. This is going to alternate sign, but this thing here is pushing it down to 0. So the limit's 0, so it converges by the alternating series test. So this was meant to give you an idea of why an alternating series that's decreasing has a sum. So I'm going to try and see if I can draw you a picture the way that they did here. Let me erase this. All right, so the idea is that, or behind this picture, is that, you start at 0 and you add the first term. So we're going to add the first term, a1, and we get some partial sum, the sum of the first term. Now the second term is going to be negative, but it's decreasing, so it's going to be less than a1. So we're going to subtract off some number less than a1. So it's going to come back bigger than 0, but not as big as s1. So when I add those together, it now will be slightly less than s1. Now I'm going to add together another number that is less than a2, but I'm going to add it, but it's not going to get me all the way back over to where I was because it's less than a2. And I'm going to end up here. And now guess what? I'm going to subtract. And it's going to get me back to some sum, but not quite to where I was before. And you see that this pattern keeps happening over and over and over again. And eventually we get really close to the actual sum of the series. So if it is decreasing, yeah, it's going to have a sum. All right, a series. Now they've added something to AP this year, so I expect that you will be tested on it. I'm expecting that. Absolute convergence versus conditionally convergent. And a series converges absolutely if not only the AN converges, but its absolute value converges. So if it's alternating and if I ignore that -1 to the n plus 1, if they both converge, it's absolutely convergent. Now, if I sum a series and I get it converges, but then if I sum the absolute value and it diverges, this is referred to as conditionally convergent. All right, it converges originally, but if I take the absolute value, it does not. All right, and we'll try to give you some insight into what that means. And your classic example of a conditionally convergent sum is the harmonic series. If I want to sum this, we already learned that, yeah, that converges by the alternating series test. But if I take the absolute value of it, well, that negative 1 to the n would go away, and you'd have 1 over n. And that diverges because it's a harmonic. So this series right here is what we call conditionally convergent, because the absolute value without the negative 1 does not converge. And there's some significance behind that. I'm not sure you're going to need to know that, but we'll look at it. And it makes sense that if the series is absolute convergence, then that implies that both things are true, so it's also convergent. And that's okay. And this is kind of interesting, and it's just something to look at, which we will look at. It says if the sum an is absolutely convergent, that means both an and the absolute value of an have a sum, then and its value is s, that means its sum is s, then any rearrangement of the terms will also have a value of s. And that seems to make sense, that it doesn't matter, you've been taught since elementary school, it doesn't matter what order you add things in. However, if sum is conditionally convergent and r is any real number, then there is a rearrangement of the terms whose value will be r. So in other words, the sum is not unique. You're not going to necessarily get the same sum when you rearrange the terms. And we'll take a look at an example. I wouldn't worry about, I have to know this, for the AP test, but it's kind of interesting to look at. We'll look at it in a minute. So it says in this example, determine whether the given alternating series converges or diverges. If it converges, determine whether it is absolutely convergent or conditionally convergent. So when I look at this series here, it's an alternating series because of the negative 1 to the n. It is decreasing. As n gets big, this is getting smaller. And the limit as n goes to infinity most definitely goes to 0. So this is convergent by the alternating series test. Now, if I look at the absolute value of this, I'm going to take this negative 1 to the n away and just make it a positive 1. So it's 1 over root n. Well, I know that for this is a p series with the power of this being 1/2 for the square root. For a p series to converge, the power has to be greater than 1. Since the power is 1/2, it diverges by the p series test. So since the absolute value does not converge, it is what we call conditionally convergent. If they both were true, it'd be absolute. So here's what's kind of interesting about this. It says a finite sum such as 1 plus 3 plus 5 plus 7 can be rearranged without changing the value of the sum. That makes perfect sense. That is not necessarily true of infinite series. It depends on whether the series is absolutely or conditionally convergent. If a series is absolutely convergent, every rearrangement has the same sum. However, if the series is conditionally convergent, it can be arranged to have any sum. So I'm going to show you an example of this. Kind of interesting that could actually happen to convince you of it. So it says the alternating harmonic series negative 1 to the n plus 1 times 1 over n, she wrote this out here, is conditionally convergent. We showed that not too long ago, right? The absolute values diverge, but this series itself converges. And can be shown to have a sum of ln 2. Now, we're not going to prove that. We're just going to take her word for it. When we get to the next unit, we'll probably be able to show you that. We can arrange the series to have a different sum. Consider the following rearrangement. Okay, so what she's done is she's taken the series, and you've got 1 minus a half plus a third minus a fourth plus a fifth minus a sixth plus a seventh minus an eighth. You see that all your terms are basically there. And there's no rhyme or reason for this, all right? It's just something that was done. And she put a set of parentheses around like 1 minus a half minus a fourth plus 1/3 minus 1/6. So you see what she did? She just grouped every other terms together. Well, I know that 1 minus a half is a half. Then you have your negative 1/4. 1/3 minus 1/6 is 1/6. And you carry this down and you get this pattern, which looks similar to what we had. In fact, if I factor out a 1/2, so I take out 2 out of all these, I get this, which is the series I started with. So now this is saying, and I knew that the sum of the series was the ln of 2, but now I'm multiplying by a half, so the sum is now changed to 1/2 ln 2. So yeah, I can't explain this. It's just kind of cool that you can sum things together and get different sums if they're only when it's conditionally convergent. But I wanted to show you that so you can see why people care. The homework is in the packet, and that should do it. Um, anyways, so I will see you guys tomorrow, and that's it.